Hi, welcome to the second part of the screencast for 10.2, 10.3. I had just begun 10.3 at the end of the first screencast regarding the addition reactions that alkenes can undergo. Just a reminder that alkenes have one double bonded carbon, and so this double bond has a sigma and a pi bond, and the pi bond, because it has to surround or work around the sigma bond, is much weaker, much more susceptible to breaking, and when that opens up, it leaves two bonding sites. So the first reaction we looked at was hydrogen coming in and filling in that site, and since hydrogen is H2, it just makes the alkene revert to an alkane. And then the second reaction we're going to look at is a halogen with an alkene, and you get what's called a dihalogenal compound. So for example, a halogen, we'll just go with Cl2. And then my alkane, I'll stick with ethene because it's the smallest, so it's easy to use. And when this double bond opens up, I'm going to have a spot on the first carbon and the second carbon, and each spot is going to get taken by one of the chlorines. So now it would be CCl H3, and I could just put a 2 around this or write CCl H3 again. And that's why it's called the dihalogenal compound, because the name for this would be 1,2-dichloroethene. As it says here, it happens quickly at room temperature. So unlike alkanes, which need to have UV light, need to have energy put in for the halogen to react with the alkane, alkenes react easily at room temperature. And when it happens, halogens have a characteristic color when they're in their pure form. Chlorine tends to have a greenish color to it. So when it reacts and forms this dihalogenal compound, it's going to lose its characteristic color. And we'll see later that's one way to identify an alkane from an alkene, is what happens when you put it in the presence of a halogen. And then the third reaction is the reaction with the hydrogen halide. And hydrogen halide sounds like it's something really complicated, but all it is a hydrogen bonded with one of the halogens like HCl or HF or HI or HBr. So we'll go with HCl as our hydrogen halide. We'll stick with ethene. And now this time, if you think about the bond opening up, you've got a spot for a hydrogen and a spot for chlorine. So one of these is going to be, you know what, I think I did this wrong on the previous one too. This is just CH2, because an alkene only has two hydrogens because of the double bond. So now when the bond opens up, I'm going to have one's going to become CH3 and the other's going to be CH2Cl. So this is just a halogenal alkane, or this would be chloral ethene. You could put one chloral ethene, although it doesn't matter because with ethene, either end is considered one. So it's really up to you. On the previous one, it's important we put 1, 2, so we realize there's a chlorine on each carbon. And this reaction also happens quickly at room temperature. The last reaction is called a hydration reaction. And this is because the alkene is going to react with water. And when this happens, you're going to end up forming an alcohol. And if you think about it, that makes perfect sense because I've got my CH3, CH3, and CH2, sorry about that. And when that bonds with water or reacts with water, remember water is really HOH. So when that happens, one of these becomes CH3, but the other picks up the OH and becomes CH2OH. So it makes sense it would form an alcohol, in this case ethanol. And this is a hugely important reaction in industry because a ton of ethanol is used every day in various industries. And one thing IB will expect you to know is that sulfuric acid is used as a catalyst in this reaction. And when we do the ester lab in class, you'll see sulfuric acid is also used as that. So I'll just give you a hint. If they're asking about an organic reaction and want to know the catalyst, if you have no idea, sulfuric acid would be an excellent guess. To finish up then, we're going to talk a little bit about distinguishing between alkanes and alkenes, and that's something called polymers. So distinguishing between alkanes and alkenes, remember alkenes are fairly reactive or highly reactive because of that double bond, but alkanes are fairly stable and need UV light to react. So an easy way to distinguish between them is to have them react with something and see which one's more reactive. So you can shake it with some kind of halogen dissolved in water. Typically it's bromine. And if the color remains, then it's an alkane because it didn't react. But if the color disappears from your bromine, which is kind of an orangey color, if the color leaves, then you can be sure it was an alkene and that it reacted to form a dihalogeno alkane. You can also burn them because alkenes have a higher carbon to hydrogen ratio, so they have less hydrogen in there. They tend to burn sootier. And alkanes tend to burn cleaner, so that would be another way of doing it, although the halogen would be a much easier test to evaluate. Last thing is that alkynes have a triple bonded carbon, and that means they're even more reactive, so they'll burn even sootier, as will aromatic compounds, which are alkanes or alkenes in a ring. They'll tend to burn really sooty. Moving on to polymers, the fact that alkenes easily undergo addition reaction allows you to take a lot of single alkenes, which we call monomers, and join them end to end to end, and you result in these just ongoing addition reactions where things, monomers keep adding to each end, and you end up with this humongous, potentially, chain of monomers, which we then call a polymer. So the example I like to think of is if you think of a person standing there with their arms crossed, that's the double bond, and then if that person suddenly throws their arms open and reaches out a hand to each side, and the person next to them on each side does the same thing, suddenly they're linking hands together, and as they join hand to hand to hand, that's the double bond opening up or breaking and then forming single bonds with the ethene next to it. And all of a sudden you have this very long polymer. So polymers often contain thousands of molecules, and they're a huge part of the plastic industry. So alkenes provide the starting material for lots of products, provides the starting material for ethanol, which is highly used, and for virtually every plastic that you use. So I'm going to look at just a couple examples here. This is just more for your information than anything. Ethene was first polymerized into polyethene. Back in 1935, it was a contamination or an accident that had happened. It forms a great electrical insulator, so practically any wire that you have with that plastic insulation on it, that's some kind of polyethene. It's also used to help develop radar during World War II. It can be really flexible, like plastic shopping bags, saran wrap, plastic wrap for food, the old school rain jackets, the cheap, rain jacket ponchos that you buy at a Twins game or whatever. This is all low density polyethylene, so it's called LDPE, but it can also be made into high density or HDPE, and that's what makes things like, water tanks, pipes, PVC, buckets like the ones you get at Home Depot, the blue recycle bins, the reusable water bottles that you could drop and don't break. So it just has a huge variety of uses. Looking at a few more uses of alkene polymers, there's one called polytetrafluoroethene, and that's just when 4 fluorines have attached to each ethene monomer. And this is known to us as Teflon or Gore-Tex. Gore-Tex is really just another application of Teflon. Teflon was actually developed by the Space Agency to help space shuttles re-enter without a lot of friction. So it's made to have very, very low van der Waals forces to make things non-stick. Nothing is attracted to it. Even geckos can't stick to this. So we know it for non-stick cookware and other surfaces. But then a company took this Teflon and used the waterproofing properties it has and used it to apply to fabrics. You can get Gore-Tex cast, whatever, but basically it gives you a waterproof fabric when you make it. And the reason why is because it forms a microporous. So microporous means that the pores in the membrane are, microscopic. They're less than a micrometer in diameter. And so Gore-Tex works on the idea that that pore, even though it's less than a micrometer in diameter, is 700 times bigger than a water molecule, but it's 20,000 times smaller than a water droplet. So that gives you an idea of how many water molecules have to be in one drop so that we can actually see a droplet of rain. What this means is when you're sweating and that sweat evaporates, those individual water molecules, which are now water vapor, can escape out of your Gore-Tex rain jacket. But when water drops, when rain hits your jacket, they can't get in. So that's how quick dry fabrics work. And Gore-Tex was the original breathable waterproof fabric, and it's a huge improvement over wearing just a polyethene rain jacket, where if you've ever worn one, it's kind of like being in a greenhouse. If you get warm, your sweat just gets trapped in there. But with Gore-Tex, that's not the case. And then some other polymers that you're probably used to are things like polystyrene is what we know as styrofoam. PVC or polyvinyl chloride is the white pipe used for plumbing. We see that white pipe all over. Polyacrylate is the superabsorbent crystal that they use in disposable diapers. And polypropylene is also used in quick drying fabrics. It's another variation of the quick drying fabrics that we have with Gore-Tex, but it's much cheaper than Gore-Tex. So this is, think Under Armour when you think of this. This is a much more budget-friendly example of quick drying fabrics. And my last point I wanted to make here that I hadn't included before, and I'm going to add, is that many plastics produce toxins that are actually called dioxins because of their structure when burned. So there are some environmental implications with it, which is one reason it's even more important that we recycle plastics rather than just putting them into the waste stream. And that really finishes up 10.2 or 10.3.